Audible to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, let me share the file. Just a minute. Okay. So before we start today's class, just to have a quick recap of what we have done earlier. Uh, so again, I start from the first class. So we started looking at the concept of different modes of heat transfer: conduction, convection, and radiation. Then what we said is, then we started looking at the conduction in a steady state conduction in one dimension, isn't it? That's what we have tried to look at. Correct. So there we have looked at the example of a slab, and in this flat slab we said that in the flat slab the cross sectional area is not changing and therefore no shell balance is required, and we directly obtain the temperature distribution across the flat slab. That is what we have done, isn't it? Then we said that in the real life application, we will not have the geometries like a flat slab, but in some cases we might have a geometries where even the heat transfer area is going to vary. And such examples are the cylindrical geometry and the spherical geometry. So in such cases, the heat transfer area is going to vary. So for such cases, we need to make a shell balance, isn't it? Unlike the previous case where we have obtained the temperature distribution directly, but in such cases, we require a shell balance because the heat transfer area, the cross-sectional area along the radial direction is going to vary. Okay, so this is the first complication we have added. Then we said that there are some cases where not only the area is varying, but also we can have the heat generation inside the medium, isn't it? And the common examples are, if you are looking at the nuclear reactor, where the heat is generated directly inside the rod. Okay. Another example could be the heat is generated in the catalyst pellet. So such type of examples are commonly seen in the real life. Even the current flowing wire, where you can see that the electrical current dissipated to uh, generate the heat, and that will be dissipated out in a radial direction, isn't it? So in all such cases, you can see that there is a heat generation taking place inside the medium, and such cases are also commonly seen in a real life application. So then we said, can we look at such situations? So we have added one more complication, and that is heat generation in the medium. Okay. So when we are looking at the heat generation in the medium, even we are looking at the flat slab, in such case also we have to look at the shell balance. Why shell balance is required? Because the Q is not going to be small q, which is nothing but the heat flux is not going to be constant throughout the flat slab when there is a heat generation taking place. So in such cases, we have to make a shell balance. Then the same thing we have extended for the case when we had a cylindrical and spherical geometry, isn't it? When we are having a cylindrical and spherical geometry, not only there is a heat generation, but also the cross sectional area, which is nothing but the heat transfer area, is also varying, isn't it? The heat transfer area is also varying. So such cases we have seen, and also we have looked at when there is a uh, composite cylinder in which the one part is generating heat, whereas the another part is not generating heat. So that is what the example which we have seen here. So current flowing through a metal wire. So this metal wire is going to generate the heat, but the insulation which is applied over the metal wire, it will not generate the heat. So this is the example of a composite cylinder, but at the same time, there is a heat generation taking place only in the metal wire. Okay, so this case also we have seen, and we have derived the equation for the temperature distribution across both metal wire as well as the insulation. Okay. We have extended this analysis further for the case with spherical geometry. Here also we have said that the heat will be generated throughout the medium, and then again we have calculated the temperature distribution, and then finally we have concluded at the end that the maximum temperature is going to be at the center. Okay, so this is what we have seen so far till now. Okay, so is there any question? Whatever we have done so far, is there any question? Hello?
No,
is it
sir.
clear to everyone whatever we have done so far?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Okay. So now today again we are going to extend our analysis further, where we are going to add one more difficulty. So far we were looking at only the steady state system, isn't it? Even though the variable area we have used, heat generation source we have added. Now we are further extending it to a case where there is a accumulation term is also present. Okay, so unsteady state heat transfer analysis also we are going to look at today. Okay, so let's see the first case here. Okay. So unsteady state conduction in a rectangular solid. So let us assume that the heat input occurs to the element through the surfaces ABGF, ADEF and ABCD as shown here. So this is the rectangular solid is there, isn't it? So in this rectangular solid, there is a heat input taking place. Again, in this rectangular solid, we are assuming a shell, a small shell which is there inside here. This is the small shell, volumetric shell we have assumed. And in this particular shell, what we are saying that there is a heat input taking place from this surfaces ABGF, ADEF and ABCD. So all these surfaces which are normal to the X, Y and Z axis, from there the heat input is taking place. Okay, clear? Can you see here? So this is the small volumetric element we have assumed, isn't it, in this entire rectangular solid, isn't it? Why we have used the small volumetric shell here? Because not only we are looking at the generation term, but also we are looking at the accumulation term. So all three complications we are looking here, isn't it? So that is why we have assumed a volumetric element here, and in that volumetric element, what we are saying that the heat input is taking place through the ABGF phase, ADEF phase and ABCD. So these are the three phases which are normal to the X, Y and Z axis respectively. Okay, so from these three phases, the heat input is taking place and the heat output is taking place from the phases opposite to these. For instance, the phase opposite to ABGF is nothing but EDCH. Okay, so the heat is taking out from the opposite phases to all these the phases which we have assumed. Is it clear to everyone what we are looking at? Is it clear? So far,
Yes.
at least the system is clear. We are trying to look at the heat transfer through a rectangular solid. Okay, and we are also considering the heat generation and accumulation term. And in order to account these, we need to make a shell balance. And therefore, we are considering a small element of volume delta X, delta Y, delta Z. So this is nothing but the small element with the volume of delta X, delta Y and delta Z. And this small element I have enlarged here in the second figure. and I am saying that the heat input is taking place from the faces which are normal to X, Y, and Z. So in this small element, the heat input is taking place from the faces A, B, G, F, A, D, E, F, and A, B, C, D, and these are the faces which are normal to the axis X, Y, and Z respectively. And the heat is going out from the opposite faces of these three faces I have already said. Okay. Now let's look at individual, faces here in this small elementary volume. Okay. Okay. So the heat input through ABGF. ABGF is nothing but this ABGF. The heat input to this ABGF face is going to be what? Cross-sectional area multiplied by the heat flux. So what will be the cross-sectional area? Remember, this ABGF is on the x-axis. So what will be the cross-sectional area? Cross-sectional area will be delta Z and delta Y, isn't it? That is going to be the cross-sectional area, correct? So cross-sectional area for this face ABGF is going to be delta Z and delta Y. So that is what we are using. This cross-sectional area will be delta Y and delta Z multiplied by the heat flux which is coming through the face ABGF. So that is nothing but QX at the location X. Is it clear to everyone? This first term?
Yes, sir.
Yes.
Similarly, the heat coming out, heat coming in through the face ADEF. ADF, this face is on the, this particular face is on this x-axis, isn't it? This x-axis along this direction, isn't it? So what will be the cross-sectional area? Cross-sectional area in this case is going to be delta X and delta Z, isn't it? You can just look at this ADEF. So cross-sectional area will be this delta X multiplied by delta Z. Okay, so the cross-sectional area is delta X, delta Z, and what will be the corresponding heat flux coming through this particular face along this line? That will be Qy at Y, isn't it? Qy at Y. Similarly, the heat coming through the face ABCD will be what? That is coming from down to up, isn't it? Something like this. Maybe I'll just show by arrow. I think, okay. Is it the slides are visible or not? Hello?
Yes.
Yes, sir. Yes, sir.
So I am just making a different color so that you will appreciate what I am trying to say here. Okay, so this is the direction of the heat input. Another will be, let me just again draw. And there is a heat input by this face also. So that will be, again, I am marking it by red. Okay, so can you see now? So these are the the heat input to the face ABGF is shown by this particular arrow, this first red arrow, isn't it? That is the heat input direction. Again, similarly, the heat input from the face ADEF is shown by the second arrow here, and the heat input from the face ABCD is shown by this third arrow, which is from bottom to upward direction. Okay. Okay, so that's what we have written here, the equation. So the heat input through the ABCD phase will be given by delta X delta Y, that is nothing but the cross sectional area for the phase ABCD, multiplied by the heat flux QZ at Z. Okay, QZ at Z. Okay, similarly the heat output, now look at the heat output. So heat output from the opposite phase of ABGF is going to be CDEF, isn't it? So the heat output will be given by delta Y delta Z at and multiplied by the heat flux QX at X plus delta X. Similarly, the heat output from BCHG, which is nothing but the opposite phase of this ADEF. So there the heat output will be given by cross sectional area, which is nothing but delta X delta Z multiplied by QY at Y plus delta Y, isn't it? Because this width is going to be delta Y. Remember, this is delta Y. So the new location will be Y plus delta Y. Okay. Similarly, the heat output from EFGH, which is the top surface here, the heat output from the top surface is going to be delta X delta X delta Y. Delta X delta Y is going to be this cross sectional area, and multiplied by the heat flux coming out from this surface, which will be QZ at Z plus delta Z. So do you all agree with this input and output term, everyone?
Yes, sir.
Okay, so now just a minute. Okay, now these are the input and output term, and there is also a generation term. So generation term will be what? Generation term is volumetric rate of heat generation multiplied by the volume of this element. What will be the volume of this element? Volume of this element is going to be delta X delta Z delta Y, isn't it? Multiplied by psi V. Psi V is nothing but the volumetric rate of heat generation. That is what we have seen in the last class. So delta X delta Y into delta Z into psi V is going to be the rate of heat generation in this element, isn't it? Correct. And the last term is the accumulation term. So accumulation term is given by what? Dou by dou T of delta X delta Y delta Z, that is nothing but the volume, multiplied by rho CPT. Okay, so this gives me the accumulation term. Dou by dou T of delta X delta Y delta Z rho CPT, that gives me the accumulation term. Now let's combine all these input output accumulation and generation terms. So our heat balance will be what? Input plus generation should be equals to output plus accumulation, isn't it? That should be my energy balance equation. So here you can see this is the input. This is the input delta Y delta Z QX at X, delta Z, X delta Z QY at Y, delta X delta Y QZ at Z. All these three terms are the input terms, minus the corresponding output terms. Corresponding output terms are what? Delta Y delta Z QX at X plus delta X, plus delta X delta Z QY at Y plus delta Y, plus Q delta X delta Y QZ at Z plus delta Z. So all these are the output terms. So input minus output plus plus generation. So generation term is going to be delta X delta Y delta Z psi V, and that should be equals to accumulation, isn't it? So accumulation is dou by dou T delta X delta Y delta Z rho CPT. Is it clear? This heat balance equation is clear to everyone? This is nothing but input minus output plus generation should be equals to accumulation. Correct. Now in this particular equation, this delta X delta Y delta Z, these are tends to 0, isn't it? Because we are taking this delta X delta Y delta Z with respect to a element, this small element which we have used here. Okay, so this delta X delta Z and delta Y, all three are tends to 0. So we can divide this entire equation by delta x, delta y, delta z. If I divide that, what we get is we directly get this dou x by dou qx by dx, because if I divide by delta x, delta y, delta z, this delta y, delta z is going to get cancelled out, and what we are going to have is qx at x minus qx at x plus delta x, isn't it? And that is going to give me minus dou qx by dx, dou qx by dou x. Do you all agree with respect to this first term? Is it clear, this first term, how this first term came?
Yes, sir.
Similarly, we will get the second term also. So that is nothing but this this second term minus the second term of the output, and divided by if you divide this entire thing by delta x, delta y, delta z, then this delta x, delta z is going to get cancelled out. So what we get is qy at y minus qy at y plus delta y divided by delta y, and delta y tends to 0. If we apply these limits, then what we get is minus dou qy by dou y, isn't it? And similarly, we will get minus dou qz by dz. And since we are dividing this entire thing by a volume, delta x, delta y, delta z, we will be left with only a psi v term here, psi v. And the right hand side, again, we will have this delta x, delta y, delta z. We have already divided this entire equation by this. So this will get cancelled out. So what we get is rho Cp dou T by dou T. And here we are assuming that rho and Cp are independent of temperature, Okay, but very often you can see that Cp etc. can be a weak function of temperature, but for a time being, we are assuming that rho and Cp both are independent of temperature. Do you all agree? Are you all able to see how we have obtained this equation number 1? Hello?
Yes, sir.
Yes.
Yes, sir.
Now in this equation number 1, all these flux terms qx, qy, qz. Qx is nothing but a flux along the x direction. Qy is the flux along the y direction. Qz is a flux along the z direction. All these individual flux terms we can represent using the Fourier's law of heat conduction, isn't it? So qx is given by minus k dou T by dou x. Qx I can replace by minus k dou T by dou x. Similarly,
Excuse me, sir.
please go ahead.
Sir, can you please explain that how did we get this del T by del small t term, time term?
This, okay. So what is
Equation
accumulation?
1.
What is accumulation?
Okay, sir. Okay, got it. Okay, thank you, sir.
See, this is the accumulation term, isn't it? Dou by dou T, del X, del Y, del Z. This is nothing but the volume, isn't it? Volume you are multiplying to a rho, that gives you a mass, isn't it? Mass into CPT, and how mass into CPT is going to be what? Energy, isn't it? How this energy changing with respect to time. That's what the accumulation term is. Correct?
Yes, sir, got it.
Okay. All right. So now, by putting this Fourier's law of heat conduction in this individual Qx term, what we get is k dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square. Again, we are assuming that this thermal conductivity K is constant along all 3 directions. Isn't it? Remember, that is what we said. When thermal conductivity is not changing along the direction, then the material is called as isotropic. Okay. Again, rho and Cp and K, we are assuming that these are independent of temperature. So that's why we have taken them out. Okay. Is it clear to everyone? So right hand side, left hand side here is K dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus psi v, and that is equals to rho Cp dou capital T by dou small t. Correct. And if we rearrange this equation, what we get is 1 by alpha. So alpha is nothing but the diffusivity. So diffusivity is given by what? Thermal diffusivity. So thermal diffusivity is given by what? Thermal diffusivity is given by K by rho Cp. K by rho Cp is the thermal diffusivity. So if I am taking this on the other side, we get 1 by alpha. So 1 by alpha dou T by dou T, and that is given as dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus psi v by K. Remember, this K we are dividing here. So we get psi v by K. So this term which is there in the bracket, that we can further denote by another symbol del square. So if we put here the del square, then what we get is dou 1 by alpha dou t by dou t equals to del square t plus psi v by k, where del square is nothing but this. Is it clear to everyone? Probably this the same equation you might have derived even in a transport phenomena, if I am not wrong somewhere, isn't it? Is it clear to everyone how we have got this equation? Hello?
Yes, sir.
Now in this equation, one more thing to look at is, see, remember we have used here accumulation term, we have used the generation term, and also we have looked at the heat transfer along all three directions. Unlike the previous cases where we have only looked at the heat transfer only in one direction. Remember the flat slab we have used, there we have looked at the heat transfer only along the x direction. When we have looked at the cylindrical or the spherical geometry, there we have looked at the heat transfer only in the radial direction. But in this particular case, the complications which we have added is, we have first added the accumulation term. Also, we have looked at the heat transfer along all three directions, isn't it? Now, so this is a generalized equation for a flat slab, because all possibilities we have included, except this rho, Cp and K are the function of temperature. Okay. We have used only these assumptions. Rho, Cp and K are the function of temperature, and these are the material is isotropic, isn't it? That is what we have assumed. Other than that, this is a generalized equation for a flat slab. Okay, and from this generalized equation, we can simplify this generalized equation based on the situation at times, and the simplified equation can be used for solving the problems if such for a particular problems, because this is a generalized equation which can be valid for all the cases, correct? So now let's look at the simplification here. So the first simplification is, let's say if there is no generation term. If the generation term is not there, if this accumulation term is not there, then what we get is del square t equals to 0. Del square t equals to 0. That means what? Dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square, that is equals to 0. And this is the standard Laplace equation. This is the standard Laplace equation. Okay. Very often we look at only the heat transfer only in two directions, x and y. We assume that in a z direction the temperature is not varying. Temperature is not varying. In such cases, we get the Laplace equation as dou square t by dou x square plus dou square t by dou y square equals to 0. This is the standard Laplace equation used for two dimension. Is it clear to everyone what we are saying? Hello? Hello?
Yes, sir, clear.
Okay. So let's make our life a little bit more complicated. So let's move to the cylindrical geometry. So far we were looking at only the flat slab as rectangular surface. Okay. Now let's look at the cylindrical surface. So this is the system shown here. There is a cylindrical, object is there. And in this cylindrical object, what we are looking at is the heat transfer in all directions. And also we are looking at the heat generation and the accumulation term here. So as I said that in such cases, we need to make a shell balance. So we have assumed a cylindrical shell here, isn't it? Small cylindrical element here. And in this cylindrical element has the thickness of delta z, and the radius is delta r, and this is located at the radius r. Okay, so what will be the rate of radial heat input through the curved surface at r? So curved surface, this is the curved surface here, isn't it? So this is the curved surface at the location r. What will be the rate of heat input here? Whatever is the surface area at this curved surface into the heat flux, isn't it? So the heat transfer area at this curved surface is going to be what? 2 pi r into dz, isn't it? 2 pi r dz is going to be the heat transfer area. multiplied by heat flux. Heat flux here is going to be what? QR at R. So do you all agree with this?
Yes, sir.
Similarly, now this is in a radial direction. We are looking at the radial direction. But what about, let's say, if we are looking at this axial direction here along the Z direction? So along the axial direction, what will be the surface area? Surface area will be, it will kind of a annular spherical type of, annular circular type of area will be there, isn't it? Correct. And what will be that annular circular area? That will be given by 2 pi r delta r, isn't it? Do you all agree?
Yes, sir.
Yes, sir.
And where we are looking at input will be here, somewhere here at qz at z, isn't it? Now both these terms we have to look at what will be the output. Now output for this radial direction will be what? The rate of radial heat output through the curved surface at r plus delta r is going to be 2 pi r delta z qr at r plus delta r. Similarly, the output from this axial direction here somewhere, the output will be what? Output will be 2 pi r delta r qz at z plus delta z. So do you all agree with this input and output terms? Hello?
Yes, sir.
Now again, similar analysis we wanted to do here, isn't it? So there is a generation term. So how we calculate generation term? We first calculate what is the volume of this element, and then we multiply by volumetric rate of heat generation. So in this case, the volume is going to be what? 2 pi r delta z. That is going to be the volume of this cylindrical shell which we have assumed here, isn't it? And multiplied by the volumetric rate of heat generation psi v, that gives me the total rate of heat generation in the element. Also, what will be the accumulation term? Accumulation term is going to be dou by dou t of volume into rho cpv, rho cpt, isn't it? So this 2 pi r delta z is going to give me the volume of this element multiplied by rho cpt, that is going to be the energy, and rate of change of energy is going to be nothing but the rate of heat accumulation in the element, isn't it? So dou by dou t of 2 pi r delta z rho cpt, that gives me the accumulation of the energy in this cylindrical shell. Do you all agree with me? Hello, is it clear
Yes.
to everyone what we are saying?
Yes,
Yes,
sir.
sir.
Okay, now again we will be making a heat balance. So heat balance is what? Input minus output plus generation should be equals to accumulation, isn't it? So this is the input term. These two terms are the input terms. These two terms are the output terms. This is the generation term, and this last is the accumulation term. Okay. Now this entire equation, if you divide by this volume 2 pi r delta z, what we are going to get for this first term? For this first term, what we are going to get is qr at r minus qr at r plus delta r divided by delta r, where delta r tends to 0. So what we are going to get is, just a minute. So here this r is also going to be there, isn't it? Because this qr is a function of r, so this r we will not be separated out. So what we are going to get is r qr at r minus r qr at r plus delta r divided by delta r. So that gives me minus dou by dou r rqr, isn't it? Do you all agree? Hello? Do you all agree?
Sir, there will be a negative sign, no, in the
So yes,
output heat term.
yes, that is
2
why
pi
see
r
here
delta
QR, correct. See this QR minus this QR at R plus delta R, this we will have to take this negative sign out. So that is why it becomes QR at R plus delta R minus QR at R divided by this entire thing, isn't it? That's why this minus sign is coming here. Is that the question?
No, sir, in the first equation, sir, there is a misprint, I am telling. Sir, there will be a minus sign, I guess. At Z plus delta Z, output heat. There should be a minus, right?
This what you are saying?
Yes, sir. This heat will be with a minus negative sign
So
because
I
it is
have taken
output.
this entire bracket here, isn't it? You can see minus sign I have put it outside here.
Okay, okay, sir. Oh.
Is it clear now?
Yes, sir. Yes.
So what we will get here is minus dou by dou r RQR minus dou by dou z RQZ plus R psi V, and that is equals to R rho Cp dou T by dou T. Isn't it? Now, in this equation, this QR we can again replace by a Fourier's law of heat conduction. So Fourier's law of heat conduction gives me QR equals to minus K dou T by dou R, and also QZ is given as minus K dou T by dou Z, isn't it? And K is, we are assuming K as a constant, and similarly rho Cp also we are assuming as a constant and not varying with temperature. So with these assumptions and this simplification, what we can obtain here is, if we put this Fourier's law of heat conduction in this equation, what we get is K, we can take it out so that this minus sign and this minus sign get cancelled out. So this K is coming out. So dou by dou R dou T by dou R plus second term here also K we can take it out, and this K dt by dz will be there here. So what we will get is KR we can take it out because here this is the function of dz, isn't it? So R we can take it out here. So that is plus KR dou square T by dou Z square plus R psi V, and that is equals to R rho Cp dou T by dou T. If you divide this entire equation by K, what we get is, we get this right hand side, which is rho Cp by K will be 1 by alpha, where alpha is nothing but the thermal diffusivity. So 1 by alpha dou T by dou T will be given as again this R is there on the right hand side. So this will be again divided. So what we will get here is 1 by R dou by dou R dou T by dou R plus dou square T by dou Z square plus psi V by K. Do you all agree with me with this equation?
Yes, sir.
Again, we can differentiate this this first term here in the right hand side, and after differentiating we can simplify. So what we can get after simplification is 1 by alpha dou T by dou T equals to dou square T by dou R square plus 1 by R dou T by dou R plus dou square T by dou Z square plus psi V by K. So this differentiation we have performed, and with this differentiation, these additional two terms which we have obtained here. Okay. Is it clear to everyone? Hello? Is it clear?
Yes, sir.
Now you can see that these are the same equation you will see in the tables which are given in the book by this transport phenomena book by Bird, Stewart and Lightfoot. Okay. So all these equations are directly given for the cylindrical and spherical geometry there, but here we are deriving all these equations. Okay. Is it clear?
Yes, sir.
Okay.
Yes, sir.
Now let us again look at the third case with the spherical solid. So spherical solid, again I am directly writing the heat balance because most of the terms are same. So input will be area into QR at R, isn't it? 4 pi r square is the area, and that multiplied by the flux QR at R, that is the input term, isn't it? Minus output term will be again 4 pi r square QR R plus delta R, isn't it? And plus the generation term is going to be 4 pi r square delta R. This is nothing but the volume of the element multiplied by psi V. So that gives me the generation term, and that should be equals to dou by dou T of 4 pi r square delta R rho Cpt, isn't it? Again, if you divide this entire equation by 4 pi delta R, 4 pi delta R, if I divide by this entire equation, then what we get is minus dou by dou R square QR plus R square psi V, and that is equals to R square rho Cp dou T by dou T, isn't it? We can put this QR again by using the Fourier's law of heat conduction. So QR is given as minus K dou T by dou R. If I put it here, what we get is K dou by dou R square dou T by dou R plus R square psi V, and that is equals to r square rho Cp dot T by dot T. And if we rearrange this term by dividing this K and taking this r square on the other side, what we get is 1 by alpha dot T by dot T, and that is equals to 1 by r square dou by dou r in the bracket r square dot T by dou r plus psi v by K. So this is the equation for the spherical geometry. We can further differentiate this, the first term in the right hand side, and by doing that what we get is 1 by alpha dot T by dot T equals to dou square T by dou r square plus 2 by r dot T by dou r plus psi v by K. So these are the three equations. This is the equation, generalized equation for the spherical geometry. This is the generalized equation for the cylindrical geometry, and this one is the generalized equation for the rectangular geometry. And these three equations, this generalized equation, you can directly use in solving the heat transfer problems. Okay, and then you can simplify it for your case and get the solution. Okay, is it clear to everyone?
Yes, sir.
This part is clear to everyone? Okay. Okay. Now let's look at okay, so far we were talking about the unsteady state heat conduction, isn't it? So unsteady state heat conduction, that means what? The temperature is going to vary with respect to time, isn't it? So the equilibrium temperature profile is yet to achieve, isn't it? Now let's look at some of the practical examples, how to solve some of the practical examples, even though these are unsteady state, but some simplification we are using in order to solve the problems easily. Okay. So there is something called as the unsteady state conduction analysis by lumped heat capacity method. Okay, so what is this lumped heat capacity method? I will explain. Maybe I'll just go to this slide first and then we will come back to the previous slide. Okay, so let us assume that you are having a solid. For a time being, let's assume that you are having a solid ball at a temperature of T naught. At a temperature of T naught. The density of this solid or metal ball is, let's say, rho. Specific heat is Cp, volume is V, isn't it? And the initial temperature is T naught. Now this solid metal ball I have suddenly put into another environment, let's say from air to a water which is having the temperature of, let's say, 100 degrees Celsius. Okay, if I put this solid directly into a 100 degrees Celsius water, what will happen? What will happen?
The temperature will start to rise.
Temperature of this solid is going to vary, isn't it? It's going to vary, isn't it? And eventually, if you give a sufficient time, equilibrium will be reached, isn't it? Equilibrium will be reached. But if I ask you what happens to the temperature at this solid surface here and the temperature here at the center, what happens to that? What happens to that? There will be some gradient with respect to the temperature at the surface. The temperature at the surface will be higher compared to the temperature at the center, isn't it? But the gradient which you look at here, this gradient between this center here and the surface temperature here, that gradient is going to be very often you will see that whenever you are using the metals, that gradient will not be too high. So very small gradient will be there. Why? Because the thermal conductivity of the metal is going to be very high. So that means the conducting resistance, the resistance for the conduction for this solid inside here is going to be much lower compared to the resistance which is present for the heat transfer by convection from the fluid to the solid. Okay, and this situation, simplifies our analysis immensely. This situation immensely, simplifies our analysis. Why? Because in that case, what you can assume that the gradient between the center here and the surface here is negligible, and you can assume this entire solid as a one single entity with a temperature of T. instead of looking at the temperature gradient from the surface to the center here. Okay, and this particular assumption is called as lumped heat capacity method. So even though there is a gradient between this surface temperature here and the temperature here at the center, but you are assuming that that gradient is very small because thermal conductivity of this solid is very high, and because of that the temperature gradient here is very small, and therefore you are assuming this entire solid as a one unit, and you are not looking at what is the conduction resistance happening here. Instead of that, you are only looking at the convection resistance which is present outside of this solid. Can you see the point? Hello?
Yes, sir.
Okay, so now let's read out whatever is written here. Okay, so then you will understand why I am bringing this example here. So if a solid, a metal ball, let's say initially at T0, is suddenly subjected to a change in environment, having a different temperature T infinity, let's say, its temperature TT is going to change. So now what this TT is this the surface temperature? Is this the temperature at the center? I am saying this TT is the temperature of this entire body. I am not looking at the temperature gradient across the solid from center to surface. We are not looking at. We are saying that this entire body temperature is TT. And why I am able to say that this entire body temperature is TT, because we are assuming this entire solid as a one single continuum unit. So its temperature TT changes with time. Some amount of time must elapse before an equilibrium temperature condition prevails. That means whatever the final temperature this body is going to achieve, there will be some time required. Now in such cases, the interesting questions people can ask. Interesting question is, if this metal ball, okay, if this metal ball which is at say the room temperature which is at let's say 25 degrees Celsius, I have suddenly put into a water which is having a temperature of 100 degrees Celsius, and I'm asking you a question, how much time you are going to take in order to reach to a temperature of let's say 50 degrees Celsius. So time, in such cases you can calculate the time required for this solid metal ball to reach to a temperature of 50 degrees Celsius by by doing the heat balance, but ignoring the heat balance across this solid. Okay. So in order to calculate the time required for body to reach a particular temperature, the analysis based on the lumped heat capacity method is used. Lumped heat capacity in the sense, why we are saying lumped heat capacity? Lumped heat capacity means entire solid we are assuming as a single unit. Okay. The discussion of transient heat conduction by lumped heat capacity analysis assumes that the system is at a uniform temperature. Can you see? So this assumption basically looks into what this considers that the entire body is at a constant temperature T, even though that constant temperature, it's not going to be a constant temperature. There will be some gradient. There will be some gradient, but that gradient we are neglecting. Why we are neglecting? Because that gradient is going to be much lower compared to the gradient which we are going to have in a outside of this solid surface. So outside of the surface there is a water present or some other medium is present. So whatever the temperature gradient is present in that particular film outside, that temperature gradient is much higher compared to the temperature gradient between the surface temperature of the ball and the center. And that's why we are assuming that it is a flat. Do you all agree? Do you all agree with what I'm saying?
Yes, sir.
So in general, the smaller the physical size of the body, so clearly the smaller is the ball, we will have a more uniform temperature here, isn't it? Instead of having a higher gradient here, isn't it? Also, the temperature distribution in the ball would depend on the thermal conductivity of the ball material and the heat transfer condition from the surrounding fluid to the surface of the ball, isn't it? So what I'm trying to say here is, It depends not only thermal conductivity, but also the heat transfer coefficient, which is outside the film, isn't it? Which is there in the outside film. Okay. So we should obtain a reasonably uniform temperature distribution in the ball if the resistance to heat transfer by conduction was small compared to the convection resistance at the surface, so that the major temperature gradient would occur only through the fluid layer at the surface. Okay, so the lumped heat capacity analysis assumes that the internal resistance of the body is negligible in comparison with the external resistance. Is it clear? Context is clear to everyone what I'm trying to say? Context is clear?
Yes, sir.
So see, a common example is this. Common example is this. If let's say a particular, let's say if you are, if you have hitted a metal ball, let's say, okay, maybe I give you another example. Suppose a particular person, let's say, died today, maybe just now. Okay, and how much temperature drop of this body takes place, let's say, after 2 hours, we can calculate using this particular methodology, isn't it? So we can assume that a body of a particular person as a cylinder, and then we can, based on that analysis, we can find out how the temperature drop is going to be there with respect to time. But here what we are assuming that the temperature inside the body is uniform, which might not be the case always, isn't it? The temperature inside the body is uniform. This assumption is valid only if the body is small and also thermal conductivity is high. If the thermal conductivity is high, in that case, what you will see that the resistance for the conduction is low. Can you see the point? So this is a common example you will see in a heat transfer books. Okay, that's why I have taken this weird example. All right.
General conduction through like heat transfer through conduction has a higher value than in convection, right? In general.
What you are saying is the heat transfer through conduction will be higher compared to the heat transfer through convection. Is that the question? But convection not only depends on the thermal conductivity, but it also depends on several other factors. So we will not be able to say in a generalized way, because in a forced convection, you can, add the turbulence and you can have the higher heat transfer there, right?
Yes, sir. Will be. Yes.
So generalized thing we will not be able to say, but thermal conductivity, you can say with the conviction that thermal conductivity of the solid is going to be much higher compared to the thermal conductivity of fluid. That you can say.
Okay.
Okay, all right. Now let us look at this particular system again little bit in more detail. So what I'm saying is there will be gradient here inside from the surface to the center, but that gradient we are assuming negligible. At what condition we can assume that negligible, that we will come to very soon. That is also a point which we have to look at. Okay, so in what cases we should ignore the internal resistance within the solid. Okay, that depends on the Biot number, but that we will come to. But let's look at the balance equation here. Okay, so what we are saying that the gradient which is there in the solid from surface to the center, that gradient we are assuming negligible. So there is a temperature, uniform temperature within this solid, isn't it? If the temperature within this body is uniform, in that case, this entire body we can consider as a single unit, and then our analysis becomes very simple. Because whatever the rate of heat input by convection will be how the energy changing with respect to this body, isn't it? So accumulation term. So that is what we have assumed here. So rate of heat input by a convection. So convective rate of heat input will be what? HA into delta T. So delta T will be what? T infinity minus this body temperature. Now there is no surface temperature here. Okay. Remember, I am not looking at the surface temperature. I am directly saying the body temperature here. So this Tt is the body temperature at time t. Initially, this Tt is T0. Do you all agree? Hello? Does it make sense?
Yes, sir.
So this will be the heat transfer to the body at any time t, isn't it? This particular term gives me the heat transfer to the body at any time t by a convection, isn't it? And that should be equal to the change in the internal energy of this entire body. So that is given as rho CPV dt by dt. Do you all agree? Do you all agree or not? So this right hand side
Sir,
equation
here-
I am able to write only because I have assumed that this entire solid is having a uniform temperature Tt. Otherwise, this right hand side equation I shouldn't, I wouldn't have able to write like this, isn't it? I have assumed that this entire body is a continuum, is a single unit, isn't it? And the temperature is uniform. So this balance equation is subjected to this assumption that the internal resistance of this solid is negligible. Do you all agree?
Sir,
Yes, please go ahead.
sir, here in this, you have not taken the heat output from the body.
So there is no heat output from the body. This entire ball is immersed in the liquid. Where is the heat output here? Heat output is, there is only a heat input here by this, isn't it? Where is the heat
Okay,
output?
sir, but like the other factors, the radiation and all, we can consider it.
Yes, you are absolutely correct. But that we have not yet looked at. When we will look at radiation, then that additional complication we are going to add. But you are absolutely true. If you are looking at the heat output by a radiation, of course, that is the term here. But that radiation factor becomes more significant when we are looking at a higher temperature. But you are absolutely true in that. Yes, that part we have not looked at so far. Does it answer your question?
Yes, sir. Okay.
All right.
So the reason, because it's inside the fluid, that is it sufficient to tell that there's no heat output, or because of the temperature outside is bigger?
No, see, here, in this case, the heat output can only takes place by a radiation. There's no other way the heat output can take place, isn't it? This entire solid we have immersed, isn't it? So from where it will go out? Tell me.
So into the fluid, from the solid to the fluid.
So fluid is already at a higher temperature.
So both the conditions should satisfy that.
So okay. So that is why you are doing this T infinity minus T, isn't it? This accounts both input and output. This is the net heat input to the body, isn't it? This net word is very important here.
Right.
Isn't it? So this T infinity minus Tt, this delta T into HA, this is the net heat input by convection to this solid. In a molecular level, you can say that the heat is transferred from the body to the fluid and the fluid to the body. Yes, of course, you are absolutely true in that. But this particular term is looking at the net heat input. Isn't it? There could be another term of output which will be by radiation, but we are assuming radiation is negligible in this case. Does it make sense? Hello?
Yes.
Okay. Okay. So now, as I said, that this equation is valid with the assumption that this entire body is a single unit and the temperature is uniform throughout the body. This is with then and then only we can write down this equation. And that means this entire balance equation is subjected to the assumption that the internal resistance of the solid is negligible here. Okay. With this assumption, this is the balance equation. We can rearrange this. After rearranging, what we get is HA by minus HA by rho CPV dt is given as this right hand side. If we integrate it, what we get is Tt minus T infinity divided by T naught minus T infinity is given as exponential of minus HA by rho CPV into T. So this equation gives me here T naught is the initial temperature of the body. T infinity is the final temperature here. T infinity is the temperature of the solid, this fluid medium which is outside here, isn't it? And Tt is how my temperature is varying with respect to time. So I can find out the temperature of the body at any time t by putting time here and putting all the parameters here. Okay. So this right hand side exponential of minus HA rho CPV T, this particular term can be rearranged and can be written in terms of two dimensionless numbers. One is the Biot number and the another one is the Fourier number. So Biot number is very important. As I said that this equation is valid with the assumption that internal resistance is negligible. And this internal resistance you can quantify using Biot number. This Biot number is very important. Okay. So it compares relative magnitude of surface convection and internal conduction resistance. Okay, so here you can see this Biot number is given by Hs by K, where H is the heat transfer coefficient, S is the characteristic dimension, and K is the thermal conductivity. Okay, so you can rearrange this equation. So after rearranging this equation, if you represent this equation slightly in a different way, what you are going to get? S by K is nothing but the resistance of the conduction divided by 1 upon H naught, 1 upon H, that is nothing but the resistance by convection. So this is nothing but the ratio of conduction resistance to convection resistance. Okay, so in a way what you are looking at, what is the rate of heat transfer by convection divided by what is the rate of heat transfer by conduction. Okay, so when the rate of heat transfer by convection is significantly higher compared to, when the rate of heat transfer by conduction is significantly higher compared to the convection, then this Biot number is a smaller value. And whenever this Biot number is small, then we can assume that the temperature within the solid is uniform. So when the Biot number is less than 0.1, then we can assume that this assumption of internal resistance is negligible is valid. When Biot number is less than 0.1, then this assumption of internal resistance is negligible is valid. So before we apply this balance equation here, first we have to calculate the Biot number, and if this Biot number is less than 0.1, then and then only we have choice of applying this equation. Okay, so whenever you have a problem of similar nature, first calculate the Biot number. Now this Biot number Hs by K, this Biot number equation is same as the equation for Nusselt number. Nusselt number is also given by Hs by K. But the only difference between Nusselt number and Biot number is in a Nusselt number K, this thermal conductivity is of a fluid. But in case of Biot number, this thermal conductivity K is of a solid. That is the difference. Okay, this is the common question asked in the interview. What is the difference between Biot number and Nusselt number? Okay, both has the same equation. The difference is the thermal conductivity used in the Nusselt number is the thermal conductivity of the fluid, whereas the thermal conductivity used in the Biot number is a thermal conductivity of solid. Do you all agree with me?
Sir?
Yes, please go ahead.
Sir, in the second step of this calculation, how have we written the RHS? I mean the denominator of RHS.
This one?
So the second step from the top.
Okay.
Yes, sir. The RHS.
Okay. All right. So see, T infinity minus Tt, this numerator is okay. This T infinity minus Tt is okay. This term, first term.
Yes.
Now what is this Tt? dt, basically we can represent this as derivative of Tt minus T infinity, because T infinity being a constant term, if I differentiate that, I will still get dt by dt, isn't it?
Yes, sir. Okay, sir.
So can I put Tt minus T infinity?
Yes, sir.
Here? Isn't it?
Yes.
So that's what we have rearranged here.
Yes.
All right. So is it clear? The context is clear why Biot number is important. Why, when this analysis we can, apply. Is it clear?
Yes, sir.
Okay. Now one more number is there, Fourier number. Now this Fourier number basically is the ratio of heat conducted to a rate of heat stored at time t. In a more, easier term, it's a relative time. It's a relative time. How I can say that it's a relative time? That also you can derive directly. Let's go back to this original equation here. Okay. This is the equation. Now this equation, this flat geometry, this is the equation which we have obtained. I can write down this equation for a one dimension, isn't it? This is for a all three dimension, isn't it? Three direction heat transfer is taking place. But let's assume that the heat conduction is taking place only in one direction, let's say x direction. Then we will have 1 by alpha dou t by dou t is given as dou square t by dou x square. Isn't it? This alpha I can take it on the right hand side. So I can write down dou t by dou t is alpha dou square t by dou x square. This is also sometimes called as Fourier second law. Okay. This is also sometimes called as Fourier second law. Now, if you rearrange the term here, so see, very often this type of equations are solved by representing all the variables in a dimensionless number. That is what you might have even studied in a transport phenomena. Remember? Do you remember the Couette flow in a transport phenomena? Couette flow in a transport phenomena?
Yes, sir.
Do you all remember?
Yes, sir.
This word have you heard in a transport phenomena ever?
Yes, sir.
Yes, sir. We have concentric cylinders.
sir.
So in that case, you can see that the dimension which you have a infinite dimension. Infinite, it's not infinite in a actual sense, but you can see that the velocity profile, becomes almost flat, and that particular length is considered as a infinite, isn't it? For a particular case. So there you can see for solving such flow behaviors, you always non-dimensionalize your equation, isn't it? Correct. So very often this type of equations are also non-dimensionalized. So if you non-dimensionalize this equation, you can see that this dou t term in the denominator, that can be replaced by you can replace this term by alpha t by s square, alpha t by x square or L square, and that L square also you can put it here on the right hand side. So you get dou square t by dou x by L whole square. So both the denominators here in the first term and the second term get non-dimensionalized. So this term here you can see the non-dimensionalized time will be given by what? The non-dimensionalized time will be given by alpha t by s square. And this alpha t by s square is nothing but the relative time, relative non-dimensionalized time. So that particular term is called as a Fourier number. What we have written. Remember this S is a characteristic dimension. So alpha t by s square, this gives you the non-dimensionalized value, and this is called as a Fourier number. Okay, so I am giving you a perspective. It is a relative time. It's a relative time, and that you can derive directly from this equation. Okay, just rearrange this equation in a non-dimensionalized form. You will get that term. All right. Is it clear to everyone? Yes or no? Hello? Hello?
So could you repeat the Fourier number once?
Okay. I am saying that the physical significance of this Fourier number is it's a relative time. It's a relative time. Why I am saying this? I am saying this because if you concentrate this particular term, let us look at this first term. So if I apply this, remember I said that this is a generalized equation. This generalized equation which is valid for all possible cases of a flat geometry. Do you all agree? Yes or no? Now let us consider a simplified case where there is no generation term and also the heat conduction is taking place only in one direction, which is the x direction. So what will happen to this equation? This psi v by k term will be omitted. Do you agree?
Yes, sir.
Also this dou square t by dou y square, this term will be omitted, and dou square t by dou z square, both these terms will be omitted. Do you all agree? So what we will be left with? We will be left with 1 by alpha dou t by dou t will be given as dou square t by dou x square.
Yes, sir.
Now what I'm saying is this time and this x, these are very important parameter. These are very important parameter because very often you try to look at the system where some of these becomes limiting. Some of these becomes limiting. That means you get the infinite or a semi-infinite type of geometry. Okay, a typical example is a Couette flow. When your velocity is going to become a same as a flat v naught, that particular length depend on several parameters, but very often you represent that particular length using some other parameters, isn't it? Instead of taking it as an infinite length, isn't it? So this non-dimensionalization is very important when you are solving such cases. So how you are going to non-dimensionalize this t and x? This alpha, I can take it inside here. So alpha t, isn't it? Can you see the point?
Yes,
Hello?
sir. Yes, sir.
So I can take this alpha inside this differentiation here. So this becomes dou of alpha t. And if I divide that by a characteristic length, let's say s square.
Okay.
So what changes I need to make it on the right hand side? I also need to divide this x by s square.
Yes, sir.
Isn't it? So what happens is by doing that, this time get non-dimensionalized, isn't it? So that becomes alpha t divided by s square. So that is a non-dimensionalized time. And here the x becomes non-dimensionalized because now you are taking x square divided by s square. Both x and s are having the unit of meter, isn't it?
Yes.
Because s is a characteristic length, correct? So you
Yes,
have
sir.
not only non-dimensionalized time here, but also non-dimensionalized the x on the right hand side.
Length.
And
Yes,
this
sir.
type of analysis you always do because when your temperature profile is going to become constant, that particular length is unknown very often. Very often that is unknown. So in order to avoid that, you represent this in terms of a non-dimensionalized number, and then you solve the differential equation, because then it becomes easy to solve. All right. Otherwise, what will happen? Your boundary condition will be what? Your boundary condition will be at x equals to infinity. Your temperature T becomes T infinity, something like that. Not clear?
So by non-dimensionalizing.
So non-dimensionalization basically get rid of that difficult boundary condition which is otherwise you have. Okay. So now if you non-dimensionalize this denominator, you get alpha t by s square. Now alpha t by s square, this entire thing is called as a Fourier number. So here dou t by this new factor dou alpha t by s square, this alpha t by s square is a dimensionless, and this is dimensionless in terms of what? Time. So that's why it is called as a relative time. You get it? And this alpha t by s square is nothing but Fourier number. So that's why Fourier number is nothing but a relative time. Make sense?
So, but on the right hand side, it is non-dimensionalized with respect to length also.
Right hand side is also non-dimensionalized in terms of x.
So that way 4 years, that will also be 4 years.
So see, here alpha t by s square is only the Fourier number, isn't it? Right hand side is also become non-dimensionalized. So what we are trying to say is when you non-dimensionalize the time, that relative time is called as a Fourier number.
So Fourier number is only used with respect to time.
Fourier number, that's why Fourier number you will always get in an unsteady state conduction. Okay.
Thank you.
Sir,
please go ahead.
Sir, how will we be able to solve ahead of that?
That we are going to look at. That is what is the next study is. This is what called as a transient heat flow in a semi-infinite solid. Okay, so this is what the equation was. Remember, that's what I said. This is what the equation I had. Correct? Hello?
Yes, sir.
Now what we are trying to say here. Let's look at the system. Maybe we will continue this in the next class, but I will give you a brief discussion on this, what we are trying to do here. So initially entire this solid block was at temperature T0. Initially this initial temperature was at Ti. Initially this entire solid block was at the temperature of Ti. Okay, suddenly this solid block we have put into some different fluid which is having a temperature of T0. So what will happen to the temperature of this solid block? the temperature profile, unsteady state temperature profile will be something like this. Can you see? Which is shown by a red colored line here. Do you all agree?
Yes, sir.
Yes or no?
Yes, sir.
I am saying initially this entire solid block, which is shown by a shaded line here, was at a temperature of Ti. I have put this solid block into another fluid which is having a temperature of, let's say, T0. Isn't it? How my temperature is going to vary across the solid? So only this one face of the solid body I have put it in the fluid. Okay, all other are outside. You get it? Yes or no? That's why we are calling it as a semi-infinite. This I have not put this entire solid directly in the fluid. I am saying that this entire solid was actually at the Ti initially, but one side of this solid I have subjected to another fluid which is at a temperature of, let's say, T0. So how my temperature profile inside the solid is going to look at, is going to vary. Will be typically like this, isn't it? Unsteady state temperature profile. Of course, if I give a sufficient time, then the temperature inside the solid block will also be a T0. But since I am saying this is a semi-infinite solid means this solid is this X is infinite. The dimension X is infinite. That's what I'm saying. Can you see the point?
Sir, so we have taken x equal to 0 at the surface of the solid.
Surface of the solid, correct. Here X equals to 0 and along this direction it is X, and this solid, the width of the solid is X equals to infinity. Does it make sense?
Yes, sir.
That's why we are calling it as a semi-infinite solid. Now what will be the typical profile in this case? See, if I put this entire solid in the fluid, then the case is different. Then the case is different in the sense that if I give a sufficient time, probably this temperature inside the solid will also be T0 in that case, correct? But here,
Yes,
that uniform temperature profile you will never achieve, because one side is infinite length, isn't it? That means you will not be able to give the infinite time, isn't it? Correct?
yes, sir.
So you will have a temperature profile, something which is shown by a red line. Okay, now let us solve this situation. Let us solve this situation. This is something called as a transient heat flow in a semi-infinite solid. So we will, since we are talking about the flat geometry, this is what the equation is there, and we are also looking at the heat transfer only in one direction, X direction. We are not looking at the heat transfer in a Y direction or even a Z direction. We are not looking at it. Okay, we are only looking at the heat transfer in a X direction. So dou square T by dou X square equals to 1 by alpha dou T by dou T. This is what the equation which we have to solve. Correct. As I said that in such cases, we have to non-dimensionalize this equation. We have to non-dimensionalize this equation. Why? Because I will not be able to apply this third boundary condition, X equals to infinity. At X equals to infinity, my temperature Ti becomes Ti minus T0 theta. This boundary condition I will not be able to implement, because what is X equals to infinity for me? Can I apply this boundary condition?
No, sir.
It's not possible to apply this boundary condition. That is why very often such situations are non-dimensionalized, so that I can get rid of this third boundary condition. Okay, is it clear to everyone?
Yes.
Okay, so let us stop here. We will continue from this point. But what I wanted to give you a message is, in such cases, non-dimensionalization of the equation is required. Then and then only you will be able to solve. Otherwise, you will not be. In fact, the same thing you do in a Couette flow. I don't know whether you remember or not, but if you don't remember, go back and see your transport phenomena book. There you will see the Couette flow, where you can see that one Couette flow between two parallel plates, isn't it? So one plate is moving with the velocity v and another plate is at the velocity 0. How my velocity profile is going to vary? Remember, that was the problem you might have seen, isn't it?
Yes, sir.
So just look at that particular example again. You will appreciate what we are trying to say now. Okay, so let us stop here. We will continue from this point onward in the next class. Is there any question? Hello? Is there any question?
No, sir.
Okay, so we will be having our tutorial on Wednesday 1 to 2. Okay. And thank you everyone for joining. Okay. Ask your friends, those who are not joining. Still our numbers is around 100. So out of 220, if hundreds are only 100 are joining, it's not good. Please ask your friends to join. And if they are relying that they will get the slides and everything from their previous batch, I am telling you all these slides are modified. Okay. All right, let's stop here.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Wednesday.
Thank you, sir.
Thank you.
Thank you, sir.